every night, while most of the house goes. Quiet, one machine keeps working. The refrigerator cycles on and off, moving heat out of an insulated cabinet so food, medicine, and leftovers survive another day. It feels ordinary because it is everywhere. But behind that familiar door is a century-old cooling idea that researchers in California believe may finally be ready for a radical alternative. The claim sounds almost impossible. Use electrically controlled ions, a salt, and a phase-changing material to create cooling without the conventional refrigerant loop. No noisy headline can prove that by itself. So this story will separate the laboratory result from the commercial promise and ask a more precise question. Could an American invention make the compressor-based refrigerator, as we know it, obsolete? The answer matters far beyond the kitchen. Refrigeration protects vaccines, stabilizes food supply chains, cools data centers, and makes modern cities livable. Cooling is infrastructure. Any technology that changes how heat is moved could influence electricity demand, manufacturing, climate policy, and the design of buildings. But first, we need to understand what the new invention is actually trying to replace. At Lawrence Berkeley National Laboratory, researchers named the concept ionicaloric cooling. The word sounds complicated, but the basic idea is surprisingly intuitive. Ions can change when a material melts or freezes. Melting absorbs heat. Solidifying releases it. If that transition can be controlled repeatedly with electricity, it can become a refrigeration cycle rather than a one-time chemical trick. A refrigerator does not manufacture cold. It removes heat from one place and rejects it somewhere else. That is why the back or underside of a working refrigerator feels warm. The cabinet is the cold side of a heat-moving system, while the room receives the heat that was pulled from the food, the air, and the components inside the machine. Most refrigerators use a vapor compression cycle. A compressor squeezes a refrigerant gas, raising its pressure and temperature. That hot refrigerant then travels through condenser coils, where it releases heat into the room. As energy leaves, the refrigerant condenses. This is the first half of a loop, designed to carry heat in one direction. Next, the liquid refrigerant passes through an expansion device. Its pressure drops, and it becomes cold enough to absorb heat inside the cabinet. In the evaporator, the refrigerant boils back into a gas. That phase change draws energy from the refrigerator interior. The gas returns to the compressor, and the same sequence begins again. The cycle is elegant, proven, and highly optimized. Engineers have improved compressors, heat exchangers, insulation, controls, and refrigerants for decades. Modern refrigerators are far more efficient than older machines. Any replacement must therefore compete with a technology that is not standing still. It must cool reliably, cost little, remain safe, and survive years of continuous cycling. The compressor is the mechanical heart. It contains moving parts, creates pressure, consumes electricity, and produces the low. Heard in a quiet kitchen. Compressors can last many years, but they also introduce vibration, wear, and manufacturing complexity. Removing one sounds attractive, yet the replacement still needs a practical way to move heat through the system. Refrigerants create another challenge. They are valuable because their boiling points and thermodynamic properties make heat transfer efficient. But a useful refrigerant must also satisfy safety, climate, compatibility, and cost requirements. The history of refrigeration is partly a history of replacing one refrigerant with another as previously hidden risks became impossible to ignore. Insulation is just as important as the cooling mechanism. Even a revolutionary heat pump cannot save a cabinet that leaks heat through its walls or door seal. Fans, sensors, control boards, and defrost systems also remain necessary. So when a headline says the refrigerator could become obsolete, It is really talking about the machinery that creates the cooling effect, not the insulated box itself. Early refrigerants included substances that were toxic, flammable, or difficult to handle. Later chemicals solved some immediate safety problems but damaged the ozone layer. Hydrofluorocarbons, or HFCs, were adopted as alternatives that do not destroy ozone. In the same way, yet many HFCs are powerful greenhouse gases if released into the atmosphere. The climate impact is described with global warming potential, or GWP. The number compares how strongly a gas traps heat with carbon dioxide over a defined period. According to the United States Environmental Protection Agency, some HFCs have GWPs, hundreds to thousands of times greater than carbon dioxide. That does not make every refrigerator an environmental disaster, but leakage at global scale matters. Policy is already pushing the industry toward lower GWP choices. Under the American Innovation and Manufacturing Act, the United States is phasing down HFC production and consumption. EPA restrictions set a GWP limit of 150 for new household refrigerators and freezers manufactured or imported beginning in 2025. The transition is real, but it does not automatically require ionocaloric technology. Many household refrigerators already use alternatives such as isobutane, and engineers continue improving conventional systems. This is an important correction to the most dramatic version of the story. Ionocaloric cooling is not racing against a frozen competitor. It is racing against an industry that can change refrigerants, refine compressors, and reduce energy use without abandoning vapor compression. Still, every refrigerant involves trade-offs. Some operate at high pressure, some demand new servicing practices, some are well suited to one application but not another. Some are flammable. The ideal solution would combine low climate impact, high efficiency, safety, low cost, and easy manufacturing. Researchers describe that balance as an unsolved landscape, rather than a single missing chemical. Cooling demand is also expanding. Hotter climates, rising incomes, urbanization, food distribution, medicine, and digital infrastructure all increase the need to move heat. A small efficiency gain multiplied across millions of devices can be significant. A new thermodynamic cycle could be more consequential still, but only if it works outside a carefully controlled laboratory. That is the opening ionocaloric cooling is designed to exploit. Instead of compressing a gas and depending on its evaporation, the cycle uses ions to alter a material's phase transition. Solid and liquid components could eliminate the risk of high GWP refrigerant gas escaping. The promise is not simply a quieter refrigerator. It is a different route through the physics of heat. The project emerged at Lawrence Berkeley National Laboratory, a United States Department of Energy laboratory managed by the University of California. Graduate researcher Drew Lilly led the experimental work, with Ravi Prasher providing the thermodynamic framework. Their study was published in Science in December 2022, and Berkeley Lab announced the result publicly in January 2023. The inspiration begins with a familiar winter scene. Salt spread on an icy road changes the conditions at which water freezes. Ions disrupt the phase transition. The Berkeley team asked whether a related effect could be controlled electrically, reversed and organized into a cycle that repeatedly absorbs and releases heat. That step turns a familiar observation into an engineering platform. In the first demonstration, the researchers combined a salt made from sodium and iodine with ethylene carbonate, an organic solvent, also used in lithium-ion batteries. Applying current moved ions through the material and changed its melting point. When the material melted, it absorbed heat. When the ions were removed and the material crystallized, heat was released. The experiment produced a temperature change of about 25 degrees Celsius while using less than 1 volt. Berkeley Lab described that temperature lift as greater than what had been demonstrated by other caloric technologies at the time. It is an eye-catching result, but voltage alone does not measure total energy consumption. Current, pumping, heat exchangers, and losses determine system efficiency. The researchers calculated that the ionocaloric cycle could compete with, or potentially exceed, the efficiency of gaseous refrigerants. Calculated potential is not the same as a refrigerator test. The demonstration established the thermodynamic concept and a measurable effect. It did not establish lifetime manufacturing cost, household safety, or performance in a full-size appliance. One distinctive advantage is that the active material becomes liquid during part of the cycle. Many solid-state caloric systems struggle to move heat efficiently into and out of a solid material. A pumpable liquid can circulate through heat exchangers, creating design possibilities closer to familiar thermal systems while avoiding a conventional volatile refrigerant gas. Berkeley Lab reported that Lilly and Prasher received a provisional patent and made the technology available for licensing. That signals commercial intent, not commercial readiness. Patents protect an idea and its implementation. They do not prove that factories can build millions of reliable units at consumer prices. The difficult work begins after a successful first experiment. The Department of Energy's Building Technologies program supported the research. That context matters because the target is broader than a kitchen appliance. The same thermodynamic cycle could potentially serve heat pumps, water heating, industrial processes, and building cooling. A platform with several markets may justify development even if its first successful product is not a family refrigerator. So the invention is real, the experiment is documented, and the physics produced cooling. The headline becomes misleading only when those facts are stretched into a product announcement. No ionocaloric refrigerator is currently replacing the machine in your kitchen. What exists is a new cycle with promising early data and a long list of engineering questions. To understand the cycle, imagine a material poised near its melting point. In its solid form, its molecules occupy an ordered crystal structure. Add the right ions, and that structure becomes less stable at the same temperature. The melting point shifts. The material can now change from solid to liquid without being heated. In the conventional sense, melting requires energy. When the phase change occurs, the material draws heat from its surroundings. That is the useful cooling step. The key is not that salt is inherently cold. The key is that ion movement changes the thermodynamic conditions under which the phase transition occurs, allowing electrical control over when heat is absorbed. Now reverse the electrical process. Remove the ions from the active region and the material's melting point shifts back. The liquid crystallizes into a solid and releases the heat it previously absorbed. A heat exchanger must carry that energy to the warm side. Repeating these steps creates a cycle. Absorb heat here, transport the material, or heat, then release it there. This is why the phrase solid-state refrigerator is not fully accurate for ionocaloric cooling. The system intentionally moves between solid and liquid states. It belongs to the broader caloric family because a controlled field, in this case electrochemical ion movement, drives a thermal response. The liquid phase is a feature because it can make the working material easier to pump. Other caloric approaches use magnetism, mechanical pressure, stretching, or electric fields. Magnetocaloric materials respond to magnetic fields. Elastocaloric materials heat and cool when stressed and released. Electrocaloric materials respond to electric fields. Each pathway can avoid conventional refrigerant gases, but each brings its own materials, force, heat transfer, durability, and cost challenges. An ionocaloric device would need more than a beaker and 2 electrodes. It requires an electrochemical cell, an active material, ion-selective elements, pumps, or flow paths, hot side and cold side heat exchangers, controls, sensors, seals, and power electronics. Every added component consumes space, money, or energy, and creates another possible failure mode. The less than 1 volt result is often repeated because it sounds like extreme efficiency. But electrical power equals voltage multiplied by current, and useful efficiency compares. Cooling delivered with total energy consumed. Without the complete system, a low voltage cannot tell us the operating cost. It is promising experimental information, not a household electricity bill. Temperature span is equally easy to misunderstand. A 25 degrees Celsius change shows a strong effect, but a refrigerator must continuously hold its interior near food-safe temperatures while rejecting heat into a warm kitchen. It must recover after the door opens, cool new groceries, make ice, and operate through changing room conditions. Dynamic cooling capacity matters as much as peak temperature change. Materials compatibility could decide the outcome. Salts, solvents, electrodes, membranes, seals, and metal components must coexist for years, without corrosion, contamination, or performance loss. Ethylene carbonate is familiar to battery engineers, but a refrigeration system imposes different flow, thermal, safety, and service requirements. The ideal laboratory chemistry may not become the final commercial chemistry. The cycle nevertheless offers an elegant advantage. It attacks the refrigerant problem at the system level. Rather than search only for another gas with better climate properties, it changes how phase transition is controlled. That opens a wider design space. It also means established refrigerator factories, supply chains, repair skills, and safety. Standards may need substantial adaptation. If ionocaloric cooling scales successfully, the first benefit could be climate-related. Solid and liquid working components would avoid the direct release risk associated with high GWP refrigerant gases. Berkeley researchers even discussed the possibility of using ethylene carbonate made with captured carbon dioxide, creating a pathway toward a working material with a favorable carbon story. That claim needs careful accounting. A material made with captured carbon is not automatically carbon negative over its entire life. Manufacturing energy, salt production, device materials, electricity, maintenance, leakage of other substances, and end-of-life handling all matter. A credible commercial product would require a full life cycle assessment, not just a carbon-containing ingredient. Noise could also improve if the design eliminates a conventional compressor. But an ionocaloric appliance may still use pumps, valves, fans, and power electronics. It may sound different rather than silent. The same caution applies to reliability. Removing one mature mechanical component helps only if the electrochemical stack and fluid system last longer. The technology may find an easier first market outside the kitchen. Industrial systems can tolerate higher upfront costs when efficiency or environmental compliance creates savings. Data centers, specialized heat pumps, laboratory equipment, or thermal management systems may provide space for monitoring and maintenance that a household appliance cannot. Successful technologies often enter through the application that values their unique advantage most. Water heating is another possibility because a refrigeration cycle is also a heat pump. The cold side absorbs energy, the hot side delivers it. By choosing which side provides the useful output, the same platform can support cooling or heating. Berkeley Lab explicitly identified water and industrial heating. as potential applications while continuing prototype development. For household refrigerators, size and cost dominate. The appliance must fit standard kitchens, pass safety testing, ship without damage, and compete in a price-sensitive market. Consumers expect years of unattended operation. A clever laboratory cycle becomes disruptive only when ordinary buyers can own it without thinking about the chemistry hidden behind the door. Manufacturing scale could bring advantages that are invisible today. Standardized cells, modular heat exchangers, and printed or roll-to-roll components might reduce cost, or specialized membranes and corrosion-resistant materials might make the device more expensive than a compressor. Until engineers choose the final architecture, both optimistic and pessimistic cost claims are speculation. The strongest case for ionocaloric cooling is therefore conditional. If the chemistry remains stable, if heat transfer is fast, if auxiliary power stays low, if materials are safe, and if manufacturing scales, the cycle could offer efficient cooling with minimal climate impact. Each if is a research program, not a footnote. The first challenge is cooling power. A household refrigerator must remove heat at a useful rate, not merely create a temperature difference in a small sample. Researchers need larger prototypes that circulate material, exchange heat, and sustain repeated operation. Scaling volume can expose slow transport, uneven temperature, electrical resistance, and pumping, losses that are negligible in a benchtop experiment. The second challenge is efficiency at system level. The active material may show an excellent thermodynamic response, while pumps, electrodes, membranes, and heat exchangers consume the advantage. Engineers measure a coefficient of performance, useful cooling, divided by the work supplied. Commercial comparisons must use the complete device under the same operating conditions as existing refrigerators. The third challenge is durability. A refrigerator can cycle thousands of times each year and is expected to operate for a decade or more. Repeated melting, crystallization, ion movement, and fluid circulation may change particle size, create deposits, degrade electrodes, or foul membranes. A chemistry that works for hundreds of cycles may still be far from appliance-ready. Safety comes next. The chosen solvent, salt, voltage, pressure, and temperature range must be evaluated for toxicity, flammability, leakage, and exposure. A final product could use a different formulation from the first experiment. Regulators will judge the complete system, including failure scenarios, transport, servicing, and disposal, not simply whether it avoids an HFC. Cost may be the hardest filter. Vapor compression components benefit from enormous global supply chains and decades of automation. Even an efficient new cycle can fail commercially if specialized membranes, electrodes, controls, or corrosion-resistant parts cost too much. Government support and licensing can accelerate development, but mass adoption requires manufacturers willing to redesign products in factories. Serviceability also matters. Technicians understand compressors, refrigerant charging, leaks, thermostats, and fans. An ionocaloric system could require electrochemical diagnostics closer to battery service. Modular replacement might simplify repairs, or proprietary sealed units might make them harder. The design choices will influence both ownership cost and electronic waste. There is also competition from improved conventional refrigeration. Natural refrigerants, variable speed compressors, better insulation, smarter controls, and stricter efficiency standards continue advancing. Ionocaloric cooling does not need to defeat the worst refrigerator ever built. It must beat the best practical alternatives available. When the new system finally reaches market, timelines should therefore remain conservative. Berkeley Lab said the team was continuing prototype work to scale cooling, improve temperature change, and improve efficiency. That language describes active research, not an announced launch date. Any claim that ionocaloric refrigerators will arrive in a specific year should be treated as speculation unless a manufacturer publishes a verified development program. There may also be applications where the technology never wins. Extremely low temperatures, very high cooling loads, mobile systems, or low-cost appliances may favor other cycles. Disruption is rarely universal. A new method can transform important niches and still coexist with compressors. For decades, just as different battery chemistries serve different vehicles and storage systems, none of these obstacles makes the invention meaningless. They define the path from discovery to product. The responsible conclusion is neither that the refrigerator is already dead, nor that the research is merely academic. Ionocaloric cooling has demonstrated a new controllable cycle. Its future will be decided by engineering data that do not yet exist publicly. So what could actually become obsolete? Not the need for a cold cabinet. We will still require insulation, shelves, doors, temperature sensors, and a way to reject heat into the room. The vulnerable component is the familiar compressor and refrigerant architecture. If a better cycle delivers the same service, the refrigerator may look similar outside while becoming fundamentally different inside. That kind of change has happened before. Technologies often keep the same consumer name while their internal mechanism is replaced. Televisions remained televisions after tubes gave way to flat panels. Cameras remained cameras after film became digital. A future refrigerator could preserve its shape and purpose while the machinery behind the hum disappears. The most credible near-term outcome is continued research, larger prototypes, new material, combinations, and licensing discussions. The most optimistic long-term outcome is a family of ionocaloric heat pumps, serving refrigeration, buildings, and industry. Between those points lies the difficult territory of durability, safety, efficiency, cost, manufacturing standards, and trust. For consumers, the winning technology will not be the one with the most dramatic laboratory headline. It will be the one that keeps food safe, lowers total cost, survives years of neglect, and can be repaired or recycled responsibly. Climate performance will matter, but it must arrive with reliability. The refrigerator is too essential to become an experiment in the kitchen. For industry, the invention is a warning and an opportunity. Companies that treat refrigeration as a finished technology may miss a new platform. Companies that chase novelty without solving heat transfer. And manufacturing may waste capital. The rational response is to test ionocaloric systems against transparent benchmarks while continuing to improve lower GWP conventional designs. The Berkeley experiment showed that electrically moving ions can control a phase change and produce a substantial temperature shift. That is the breakthrough. Everything beyond it remains a contest between physics and engineering. A single volt may move the ions, but only years of testing can move the technology from a laboratory bench into millions of homes. America's new invention will not make cold storage obsolete. It may, however, make today's method of producing cold look unnecessarily complex. If ionocaloric cooling becomes efficient, safe, durable, and inexpensive at scale, the compressor's familiar hum could eventually sound like a relic from an earlier age. Until then, the honest verdict is both exciting and restrained. The old refrigerator is not dead, but for the first time in years, a genuinely different thermodynamic cycle has earned serious attention. Would you trust a refrigerator cooled by controlled ions and phase-changing material instead of a compressor and refrigerant gas? Tell us what would convince you.